And perhaps you can say a few words. How are you today? And then you can start, please.
Brilliant. Brilliant. Thank you, Janos. So thanks for inviting me to give another FRK seminar. I think this might be my fourth FRK seminar, I think, possibly. And it's always a pleasure to talk to you. And this is the first time I think I'm giving this seminar from Lancaster, which is where I'm now based in the northwest of England. And as you can see, those are all my current affiliations down there at the bottom. So I'm going to talk to you today. The title of this talk is actually also the title of an, oh, sorry, excuse me. Let me just switch this off for a moment. Is also the title of an archive preprint with Elisenda, who many people here know. And there's the archive identifier. Actually, I just put an updated version on yesterday, which hasn't quite made it through. So the version on archive at the moment is slightly outdated. But I should say that the ideas in this work, although they're kind of captured in that paper, many of them actually arise from work on bifurcations with Balázs and József, who everybody knows really. And I'm also going to just kind of mention in the context of some examples, some recent results on bifurcations which haven't yet been archived, which hopefully soon will be archived, which are slight extensions of some of what we did in this paper. I'm largely going to skip over giving you those introductory slides where I say this is what a mass action network is and this is why it's interesting and so forth. I'm going to kind of assume that people know what mass action networks are, but of course you're very welcome to interrupt me. And I'll kind of go into more detail on anything that I say too quickly. So let's do this by example. So here's an example of a mass action network. We've got two species, chemical species X and Y. This network has 4 chemical reactions. Each of those chemical reactions is associated with a rate constant, kappa 1 to kappa 4. We can draw these chemical reactions or this network in a couple of different ways. I suppose you could say this is like the traditional way of drawing it, just as a sequence of reactions, or we could put all of those reactions into the so-called Euclidean embedded graph and draw it this way. So there's a couple of alternatives that we have there. What are the key quantities associated with this reaction network? Well, first of all, a little bit of terminology. So it's a 2-4-2 network. That first 2 refers to the number of species. The 4 refers to the number of reactions. And the final 2 refers to the rank of the stoichiometric matrix. And the stoichiometric matrix tells us about the net production and consumption of species in each of those reactions. So each vector is a reaction vector. Each column vector is a reaction vector. We can write the mass action system, that's that system of differential equations that comes out of this network in this very kind of abbreviated form, kind of useful form there, where we have the stoichiometric. We have the stoichiometric matrix at the start, and then we have a vector of reaction rates, kappa x to the a. Kappa is this vector of rate constants. This little circle there is just entry-wise multiplication, and then x to the a is just a vector of monomials. So I think all of this is kind of familiar to people here. So just to set the scene, one useful quantity is to collect the exponents of the monomials into an exponent matrix, which I'll call A in this talk. I think somebody's got their mic on, so there's a bit of feedback coming on my end. Anyway, so we can collect the exponents in this matrix A, and so those exponents just reflect what's going on the left-hand sides of these reactions, so the source complexes of these reactions. And this particular reaction network, we'll say, is quadratic, which means that the monomials are at most quadratic. Equivalently, the row sums of A are at most 2. equivalently, in reaction network terms, all the source complexes are at most bimolecular. Okay, so that's just kind of to set up a little bit of terminology. But actually, what might be quite useful to do, I thought, is to use this network as a little example of the kind of calculations we'll do before I actually justify why we might do these calculations in order to make some claims about why we might do these calculations. So the first claim is that I would like to make is that no network with these particular source complexes, the source complexes being 0, x, 2x, and x plus y, no network with those source complexes, two species network, rank 2 network, but it doesn't matter how many different reactions we have, can admit more than 2 positive non-degenerate equilibria. And rather than trying to justify that fully, I'll just kind of tell you what are the calculations we need to do in order to verify that claim for this network, because then this calculation will make sense later when I present the general argument. So the first thing that we're going to do is we're going to take the exponent matrix of this network A and augment it with a column of 1s. And then we're going to look for vectors which are in the kernel of the transpose of that matrix. And we're going to put them as the rows of a new matrix. Let's call that matrix W. And in this case, in fact, because that augmented exponent matrix has rank 3, there's just up to scaling 1 vector in W, 1 row of W, and we can choose it to be an integer vector of this form. And you can check that in fact W times augmented A equals 0. So where does this claim that no network with these sources can admit more than 2 positive non-degenerate equilibria come from? Well, what calculation does it come from? Well, it comes from the calculation that the sum of positive elements of W is less than or equal to 2. That, it will turn out, implies this claim. How that comes about is something that I'll expand on. Okay. So let's just do a few more kind of calculations with this network. So the next thing that we're quite often going to be interested in calculating is we're going to be interested in calculating a basis for the kernel of the stoichiometric matrix gamma. So here I've taken the stoichiometric matrix and I've written down 2 vectors and I've put them as columns of a matrix. And the 2 columns of this matrix are 2 linearly independent vectors in the kernel of gamma. I haven't chosen them completely arbitrarily. I've actually chosen them because these are precisely the 2 vectors in the kernel of gamma which lie on the boundary of the non-negative orthant in R4. And the reason for doing that is because this gives me a nice, easy way to parameterize the positive part of the kernel of gamma. So this will turn out to be important. It's what we'll call the positive flux cone of the network. So I can parameterize this positive flux cone by taking a convex combination of these 2 vectors, V1 and V2, which form a basis of kernel of gamma, and which happen to lie on the boundary of this code, in fact. So if I do that, I get this vector, which depends on some parameter alpha, and as we vary alpha, it crosses through a section of the positive flux cone. So pictorially, we've taken a kind of straight, flat cross-section of the positive flux cone here. And if we want to get any point in the positive flux cone, well, all we have to do is we have to scale vectors in this cross-section by some other parameter, let's say lambda. So what we've really managed to do by doing this in a very simple way is just find a parameterization of the positive flux cone of this network. I apologize to people who are very familiar with all of this, as I know many of you are, but just I'm going to say it all for completeness. Now, once we've written down this function H alpha, or this parameterization of a cross-section of the positive flux cone H alpha, we can write down an equation, which is what we're going to refer to as the solvability equation, which is H alpha to the W is equal to kappa to the W. Now that looks a little bit obscure. That's maybe a little bit less obvious where that comes from, but I will kind of expand on where that comes from in a bit. But let me show you what it looks like for this network first before doing that. Slightly annoying. Okay, there we go. So for this network, what is this H alpha to the W? What is this solvability equation? Let's write it as H alpha to the W minus kappa to the W equals 0 look like? Well, H alpha is this vector here, and we're raising it to the power of this matrix. I'm using kind of fairly standard notation here. So that just means I multiply the first element of my vector by the first element of the matrix and so forth. And when we do all of that, we just get this expression here. And when we simplify it and we clear denominators, we end up with a single quadratic equation, which looks like this. Theta is a combination of the parameters. It's kappa 1 squared over kappa 2 kappa 4, which is precisely this kappa to the W quantity. Now, this equation is a quadratic equation because the variable of interest is alpha. It depends on one parameter, theta, which is a combination of the rate constants kappa. And the fact that it is at most quadratic is important because we're going to say that, or argue that, in fact, the positive equilibria of this network correspond in a very nice way to the zeros, to the solutions of this equation. And because it's a quadratic equation, we can have no more than two non-degenerate zeros of this equation. And it's from that claim, from that observation, that the claim that you can have no more than two positive non-degenerate equilibria comes for this network. And again, of course, I will expand on all of this. Another set of claims that we can make, again, just by looking at this so-called solvability equation for the network, is about the parameter sets for multistationarity. So here we can argue that there are no positive equilibria when this quantity theta is less than 12, that there are two positive non-degenerate equilibria when this quantity theta is greater than 12, and that when theta is equal to 12, we have a non-degenerate fold bifurcation unfolded by the rate constants kappa. And in terms of actual calculations, the last claim, in particular the claim about non-degeneracy and transversality, follow from very trivial calculations on this quadratic equation, so on this function f, calculating its second derivative with respect to alpha and its first derivative with respect to theta at the bifurcation point and checking that those are non-zero. Another thing that we can do, and I'll kind of slightly skip over some of the details on this because I'm going to show it to you in the abstract anyway, is we can parameterize the positive equilibrium set. So in order to do this, we're going to need to compute another quantity associated with this matrix A1, the augmented exponent matrix, and that is this matrix, which I've called G here, which is a generalized inverse of A1. In fact, this generalized inverse in this case is a left inverse because A1 is an injective matrix. It's got trivial kernel. So once we've computed this generalized inverse, we will show that the positive equilibria of this network are precisely the set of points x of the form of this form here that I've underlined, H alpha over kappa to this matrix G hat, where alpha lies in this set A kappa. So there's a couple of details here that I've kind of missed out. One missed out saying there on the slide. The first is, well, I'm writing A kappa as the solution set of that solvability equation that we wrote down earlier. So the set of alpha which solves that equation for any particular value of theta, or kappa in this case. And I'm writing this G hat to refer to the top two rows of G, which also actually happen to be well, it doesn't matter. Okay, so just the top two rows of this generalized inverse of A1. So with this notation, again, let's expand out what that actually means in terms of a parameterization. We're just doing the usual thing. We're raising a vector to the power of a matrix, entry-wise in the usual way. We end up with the vector looking like this. But we also have this additional information that alpha belongs to this set A kappa in there. And, sorry, excuse me, When we take that into account, if we do a little bit more manipulation, we can write down exactly X and Y, the equilibria for this network, or two branches of equilibria for this network. So we've got a parameterization of equilibria out of this process. This would have been very easy to, or fairly easy to derive in any case, directly from the mass action equations, but I just wanted to say that I'm more interested in the way we derive it in this particular instance than the fact that it was quite easy to derive in other ways. So what's the general idea? Well, the general idea is that what we saw in this simple example actually extends to any mass action network, including networks with conservation laws. We can always obtain these parameterizations of equilibria. We can write down alternative systems of equations, and we can use all of this to make claims about the geometry of the equilibrium set, about the number of positive non-degenerate equilibria on stoichiometric classes, and about bifurcations. There's another kind of small point, which I'll kind of mention, but not emphasize too much, which is that the alternative equations may be simplified if the network factors over a partition. So I'll say something about partitions and conservation laws, the two kind of additional things that I mentioned on that previous slide. So first of all, conservation laws, we all know that reaction networks generally have conserved quantities, that the vector field is always parallel to the image of gamma, so the stoichiometric subspace as it's known, that the intersection of cosets of this stoichiometric subspace with the positive orthant are termed positive stoichiometric classes or positive stoichiometric compatibility classes. These may be bounded or unbounded, and that we can write down the defining equations of one of these well, by first of all insisting that we have a positive point and then insisting that some set of linear equations is satisfied, say, of the form Zx equal to K. So this matrix Z here is just encoding the linear conservation laws. Its rows are a basis of the kernel of gamma transpose, and K is just some constant vector. Okay, so we have conservation laws in general, and they do complicate the analysis a little bit, but not too dramatically in this case. We also might have partitions of the network. So this is maybe slightly less familiar, but let's take an example. Let's take this little network here of 2 species, 4 reactions, and rank 2. Here is, sorry, I've written two species. It's actually 3 species, excuse me, in this case. So that's a 3-4-2 network, 3 species, 4 reactions, rank 2 network. In this case, if we look at the kernel of gamma, we can see that the basis of the kernel of gamma is actually given us by these 2 vectors, 1, 1, 0, 0, and 0, 0, 1, 1. And these 2 vectors have disjoint support. So the support of the first vector is the first 2 entries, and the second vector is the last 2 entries. And this is really what it means to say that this network factors over the partition 1, 2, 3, 4. So where we've divided the 4 reactions into the first 2 and the last 2. It just means that the kernel of gamma is the direct sum of its projections onto the coordinate hyperplanes associated with blocks of the partition. So we'll come back to this idea a little bit later. So now let me say where all of this is coming from. Let me kind of go through the partition, go through the construction, but what I'll do is I'll only go through this for the case of the trivial partition, because otherwise the notation gets quite messy if I try to do this for a general partition. So now throughout what's going to come, we're going to work with an arbitrary n species M reaction rank R network. The first quantity that we are interested in, I've already mentioned it, so that's the nice thing about having seen the example. The first quantity we're interested in is the positive flux cone. So this is just the intersection of the kernel of gamma with the positive orthant in Rm. We'll always assume that this is non-empty, because when it's empty, where we don't have any positive equilibria at all, we can't have any positive equilibria at all. Such networks are called dynamically trivial. In some literature, there are other terms for that, but they're not very interesting, and that's the important point. So let's assume it's non-empty, in which case its closure is a convex polyhedral cone of dimension m minus r, number of reactions minus rank. So what do positive equilibria satisfy? Well, first of all, they have to be positive, so they satisfy that they live in the positive orthant. Secondly, if we assume that they live on some particular stoichiometric class satisfying an equation of the form zx equals c, then they have to satisfy that equation, obviously. So those are the kind of two, if you like, trivial bits of information. But the key thing that they have to satisfy is that this reaction rate vector, kappa x to the a, lies in the positive flux cone. And that's what we're going to work with now. So in order to work with it, we need to parameterize the positive flux cone. And we do this very much as we did in the example, which is that we choose a flat cross-section of the positive flux cone. Let's call this C hat here. We choose some cross-section of it. We parameterize that cross-section. And we can do this in really any way we choose, the way that I showed you, where we choose some vectors on the boundary and we take convex combinations. Well, that'll work if your cone is simplicial, and you can find other ways if it's not. In any case, we find a flat cross-section. We parameterize that cross-section by a parameter which we'll call alpha, which lives in some space which we'll call y. And then we can write any point in the positive flux cone simply as a scaling of h alpha. So h is the actual parameterization of this flat cross-section, and lambda is just a scalar, a positive scalar, which tells us where we are on some particular ray, which passes through some particular point on this cross-section. So these two quantities, lambda, this scalar, and alpha, this point in our space y, between them, they tell us where we are in the positive flux cone. So each alpha is actually associated with a ray in this flux cone. Okay, so once we've, so the equation that we're interested in, or the kind of property that we're interested in, is that these rate vectors, this rate vector should lie in the positive flux cone. But that's the same as saying that this rate vector is equal to lambda h alpha, if we've found a way of describing points in the positive flux cone in this particular way. And now if we take logarithms of this equation and do a little bit of rearranging, we end up with this, what is essentially a linear equation here. So this linear equation that we end up with, well, this is just a matrix. This is the augmented exponent matrix. And these are just constants because we're assuming for the moment that we're working with constant kappa. This is okay, it depends on alpha, but it's just a vector for the moment. That's all we're interested in. And this is just, let's say, also some vector. Okay, so we've got a linear equation, which is of the form vector plus matrix times vector is equal to vector. So I need to just take a tiny kind of digression into some basic linear algebra to kind of say the next part easily. So supposing you do have an inhomogeneous linear equation of this form matrix times vector is equal to vector. What does it mean to solve this linear equation? Well, first of all, we need to confirm that the right-hand side vector v does indeed lie in the image of M. We can do this by what's sometimes called the Fredholm alternative, which is just the image of M is just, in fact, the transpose of the kernel of, the orthogonal complement of the kernel of M transpose. So we can write down a set of vectors which are a basis for this kernel of M transpose, and we can check that all of those are orthogonal to V. All the point of this is just that we can write down a matrix condition which ensures that V is in the image of M, which is of the form WV equals 0, where W is precisely this matrix we were thinking about earlier. Its rows are a basis for the kernel of M transpose. So we'll call this equation WV equals 0 the solvability equation. So that's a necessary and sufficient condition for the existence of solutions. If the solvability equation is satisfied, then we solve this equation like we would solve any linear equation. We find a particular solution, say U naught, and then the general solution is just U naught plus the general solution to the homogeneous equation, which is just the kernel of M. How do we get a particular solution? Well, one way to do it is we write down a generalized inverse of M, let's say G, and then our particular solution U naught would just be G times the vector V. So that's one way of getting a particular solution to this equation. And then if we want to write down the general solution, it's also useful to have a matrix Q whose columns are actually a basis of the kernel of M. And then we can write down the general solution in this nice simple way, which is we get GV, that's our particular solution, plus QW, which just kind of ranges over the kernel of M. Okay, so that's just some linear algebra. There's nothing particularly to do with chemical reaction networks and all of that, but let's go back to the linear equation that we were looking at before and just apply all of this. So the first thing is we want to know the kind of solvability condition. What does the solvability condition for a solution to exist for this look like? Well, it looks precisely like this. We write here W just has the same meaning as it had before. It's a basis, its rows are a basis of kernel A1 transpose. And the solvability equation that drops out in this particular case takes this form. And if we exponentiate both sides, everything here is positive, kappa is positive, and H alpha is positive. Otherwise, these logarithms wouldn't make sense. So we can exponentiate everything here. We get back to this equation. So we'll kind of abuse notation or terminology a little bit and call this equally well the solvability equation. Or in fact, most often we'll actually clear denominators in this and refer to the resulting polynomial system as the solvability equation. So yeah, that's, I suppose, a remark, which is that W can always be chosen to be an integer matrix. So this equation, H alpha to the W equals kappa to the W, is always a kind of rational function on the left, a constant on the right. We can clear denominators and we end up with a polynomial system. Okay, so that's our solvability equation. Now, suppose that we satisfy the solvability condition. So in order to kind of talk about that, we need to think about the zero set of the solvability equation. We'll give that a little bit of, we'll kind of denote that as A kappa here. So this is the solution set of the solvability equation. It's a set which lives in this parameter space Y, which parameterizes a cross-section of this flux cone. So let's suppose that alpha belongs to this parameter space Y, and so this equation can be solved for some particular value of kappa. Then we can just follow the procedure above and get the general solution of that equation. And the general solution looks like this. The unknown vector, if you like, was this thing here on the left. This G was a generalized inverse of A1. This Q was a matrix with whose columns are a basis of the kernel of A1, and mu is just some arbitrary positive vector. So we end up with this general solution, just following using some basic linear algebra. And we're actually not interested in lambda, we're interested in x. So we just take the top n rows of this system of equations that we've written down of the solution. And this top n rows just gives us the log of x in terms of alpha and mu, and kappa as well, obviously. And if we exponentiate again both sides of this equation, we end up with x is equal to something in terms of alpha and mu. And this is a crucial quantity. We'll call this function of alpha and mu f kappa because it does depend on kappa as well. But in most calculations, we're assuming kappa is constant, with the exception of some of the calculations connected with bifurcations where we allow kappa to vary as well. So what have we ended up with? I'm just summarizing, not saying anything new here. We've ended up with the fact that positive equilibria of this arbitrary mass action network can be parameterized in this particular way, which I've written down as this kind of equation star. But hopefully it looks a little bit less obscure now because I've explained where it comes from. So the key thing is that we've got these two parameters, alpha and mu. Alpha belongs to this set, which we called A kappa there. Mu belongs to the positive part of some Euclidean space. Mu just tells us where we are in the kernel of this matrix A1. And between them, those two parameters give us the positive equilibrium set of an arbitrary mass action network. And one feature of the way that I've written this down is that it presents this positive equilibrium set as a disjoint union of toric sets. What I mean by that is if you fix any alpha, so this just becomes a constant, then you have a a set of the form constant times mu to the q hat. So mu to the q hat, this is just a vector of monomials here. So we have constant times vector of monomials, Laurent monomials. So we have a disjoint union of toric sets, and if in particular A kappa just consists of a single point, then we have a toric set, and we can say that the equilibrium set is toric. If A kappa is just finite rather than being equal to 1, then we have something which is locally toric, as in the neighborhood of any particular equilibrium, the equilibrium set is toric. Okay, so we can parameterize the equilibrium set using these techniques quite easily. If we take a step back and think about what we've done so far, well, we've kind of found a way of describing the equilibrium set of an arbitrary mass action network, but along the way to get to that, we also had to assume that the solvability equation was satisfied. So we had this equation here, the solvability equation. And now supposing we're interested in equilibria which lie on some particular stoichiometric class satisfying these linear equations here, then what do we have? Well, we have a pair of equations in alpha and mu, one of which is the solvability equations, which is actually just an equation in alpha, really. And then one of which is the second equation, which just tells us that this equilibrium belongs to some particular stoichiometric class, which is an equation in alpha and mu. And when you take this pair of equations, this is what we'll now refer to as the alternative equations for this system, for equilibria, positive equilibria of a mass action network. Yeah, so I think I've said what those two bullet points are saying. The first one is the solvability equation, and the second one tells us that the conservation laws are satisfied. I've put it down a little bit more formally here. So we're actually interested in this function f kappa, which is the parameterization of positive equilibria here. And so we want to make a few claims about this function. First of all, it's smooth, it's injective, and it's semi-algebraic. And it takes positive equilibria on some stoichiometric class or it takes this set of alpha and mu, which solve these alternative equations, to positive equilibria on some stoichiometric class. So that's the first claim. The second claim is that it also tells us about degeneracy and non-degeneracy of solutions. So degeneracy and non-degeneracy of solutions of this alternative set of equations correspond precisely to degeneracy and non-degeneracy of the original equilibria that we were interested in. So it preserves degeneracy and non-degeneracy as well. Actually, we can say quite a lot more than that, but I mean, that's what's there in the paper at the moment. So that's all I'm going to say in this formal sense at the moment. How does this generalize very briefly if you have a non-trivial partition? So supposing you have a network which factors over some partition like this, it's got 4 reactions, and the kernel of gamma can decompose into a part supported on the first 2 and a part supported on the last 2 reactions. Well, in all the arguments where we had this vector of 1s before, we're going to replace that with a matrix where we've projected that vector of 1s onto the 2 relevant subspaces associated with the partitions. These various quantities that we've defined all have the same kind of linear algebraic meaning, except for the fact that we've replaced wherever we before had A augmented with a 1, we've now replaced it with A augmented with a 1p. So this kind of augmented with this matrix here on the right, and we get exactly the same parameterization. We get the alternative equations are exactly as before, and so forth. So really, the changes are, in some formal sense, very, very marginal if we work with a partition which is not just the trivial partition. So we have a non-trivial partition. I just want to make a couple of remarks about this whole construction. First of all, this alternative system of equations is a square system. It's got the same number of equations and variables, and that is the number there, which I suppose we're most interested in the case where that number is considerably less than n, the number of equations of the original mass action network, or the equilibrium equations of the original mass action network. Another remark is that these matrices which came up in this construction are not in general unique. Sometimes they are effectively unique. So for example, G hat might actually be an ordinary inverse rather than a generalized inverse, in which case it is uniquely defined. But in general, there might be some scope for choosing these matrices. And also there are various interesting special cases where some or several of these matrices are empty. We can always choose Z, W, and Q hat to be integer matrices. G hat may or may not be an integer matrix, but if it is, then all of these alternative equations are polynomial equations. If G hat is not, if we can't choose it to be an integer matrix, then we still might be able to write down an equivalent polynomial system, but we might have to do a little bit more manipulation in order to do that. Okay, so just to continue with a couple more examples, let me go back to this one which involves a non-trivial partition. So in this case, this 3-4-2 network with a non-trivial partition, I'm just reminding you of the network on this slide, reminding you of the fact that kernel of gamma factors over this partition 1, 2, 3, 4 there, which just tells us about this basis of the kernel of gamma, which has two vectors with disjoint support. So that means that we are interested in this matrix A1P here. So instead of just A1, we replace the 1 with 1P. And in this case, if we observe that this matrix has rank 4, so W is empty. Remember, W is the kind of matrix which sits here and multiplies A1P and gives us 0, but in fact, there's no vectors in the left kernel of A1P. So W is empty. On the other hand, Q is the matrix which sits here, the kernel of A1P, and that consists of a single vector up to scaling, which we can write as 1, 2, 2, minus 2, minus 4. And out of it, if we just apply the theory that we've just seen, we get a monomial parameterization of positive equilibria. So in this case, the positive equilibrium set is toric. We've got this one parameter mu, so it's a toric ray. And it's actually really trivial to see from this parameterization that each positive stoichiometric class has a unique non-degenerate equilibrium for all parameter values, for all rate constants kappa. Yeah, so that's kind of completes, I suppose, analysis of that example or of the interesting things in that example. Here's a slightly more complicated example, also a 3-4-2 network, but this time which doesn't factor over a non-trivial partition. Follow the same procedure. We end up with a parameterization of positive equilibria, which looks a little bit more complicated, of this form here. But still just one parameter alpha. As usual, these quantities theta now are combinations of rate constants. In fact, if I were to write it down more precisely, theta is just equal to the rate constants to the minus g. Sorry, that should be minus g, not g hat. And these are the first three components of kappa to the minus g, theta 1, theta 2, and theta 3. So just combinations of rate constants. But anyway, to cut a long story short, if we just write down the alternative equations, it's just a single equation in a single variable alpha, which lives in 0, 1, and with some parameters, theta 1, theta 2, theta 3, and k, which tells us which stoichiometric class we're on. So everything has become a lot easier in terms of the analysis of when this network, say, admits 1, 2, or 3 isolated positive equilibria. So we can exactly write down conditions for when that can occur. We can write down conditions for when so-called cusp bifurcations occur. So I'm not going to say anything about what cusp bifurcations are. They'll come up in a variety of other talks by Balázs and Joseph and myself, because we're thinking about them quite a lot at the moment. But I just want to mention that we can find very explicit parameter descriptions for when cusp bifurcations occur as a side effect of doing these calculations. And so I just thought I'll complete the calculations for this example and see what we get. So in this particular case, it's quite easy to write down explicitly the set of cusp bifurcation points for this network, parameterized in terms of 3 parameters. I'm calling them alpha, beta, and gamma here. And we can say that a cusp bifurcation occurs when x, y, z is equal to some particular combination of alpha and beta, and when the rate constants are as follows. And the non-trivial bit of this, I suppose, is the claims that the cusp bifurcation is non-degenerate and that it's unfolded by the parameters kappa, by the rate constants kappa. If you do those calculations which tell you that in terms of the original mass action equations, they get rather difficult. If you do those calculations in terms of the alternative single mass action equation, they're actually quite easy calculations. But that's quite a long story, so I won't say very much more about that, but I just want to say that it does really simplify the calculations associated with bifurcations quite a lot. Apart from looking at examples, we can also kind of have some bigger, I suppose, theoretical consequences we can mention. So I've put down a couple of these, but these are not, there's nothing very special about these ones. We've got a lot in our preprint, different kinds of consequences. So here's one consequence. If the source complexes, let's just think about this in the case where we've got 2 species, and let's suppose the source complexes of a reaction network like this one here all lie on a line. So this time we've got affinely dependent source complexes. Whereas on the other hand, the reaction vectors don't all lie on a line. So the reaction vectors actually span a 2-dimensional space, while the affine hull of the source complexes is 1-dimensional. Then networks with that property, where the dimension of the affine hull of the source complexes is less than the rank of the network, are kind of uninteresting from several points of view. So in particular, positive equilibria don't exist for most parameters. They only exist for an exceptional set of parameters. And whenever they do exist, they're always degenerate. In fact, they're strongly degenerate. So these are examples of degenerate networks, but the degeneracy criterion is a very geometrical one. And this claim comes out of looking at the alternative equations, comes out quite easily from looking at the alternative equations. Here's another little consequence. So this is a particular class of networks, quadratic, n-species, n-reaction, rank n-1 networks. And we can easily argue, for example, that this class of networks admits no more than 2 positive non-degenerate equilibria on any stoichiometric class. How do we argue that in brief, very briefly? Well, the alternative equations this time just take the form of a single equation, which looks something like this. There's only one scalar variable in there, which is mu. And if you examine the form of this equation for quadratic networks in particular, you can prove that it can never have degree more than 2. So it's always a quadratic equation at most. And hence it never admits more than 2 non-degenerate solutions for this class of networks. So it's a easy consequence of the theory. This would be an example of an easy consequence of the theory. Here's a slightly less easy consequence of the theory, which I'm not putting as a theorem in particular, but more as a general kind of procedure. So given any quadratic n-species m-reaction rank n network with no more than n plus 2 distinct sources, so we can have as many reactions as we like, but we can't have too many source complexes, then we can easily compute bounds on positive non-degenerate equilibria. And this is one of the bits of preprint which I quite like, but which is also rather long to go into, so I won't go into it. But I just want to say that these bounds arise by thinking about a class of graphs called SR graphs, which we can associate with the network. And these are graphs which we've thought about previously in other contexts. And in fact, the bounds come about by thinking about labelings of SR graphs associated with the exponent matrices of these networks. So I won't go into the details, but that's kind of like the spirit of where they come from. Final little kind of example of a result, and this one is not in our paper. This is one which is kind of not yet written down really, but is kind of quite easy to see in some ways, filling in a couple of gaps in the proof. proved a little bit difficult. But this is, let's say you have quadratic n species, n+1 reactions, rank n-1 networks with affinely dependent sources, then you actually can't have cusp bifurcations in these networks. So again, how do we know this? Well, we know this by examining the alternative equations. It's far from obvious just looking at the original mass action equations. It's not exactly obvious looking at the alternative equations, but we can kind of infer it from the alternative equations, although it takes a little bit of proof to complete the claim. And it's a slightly subtle result because in this case, these networks can admit cusp points. They can admit cubic singularities, but those can't be fully unfolded, even though the networks have, in theory, enough parameters to allow cusp bifurcations. Okay, I think that kind of brings me to the end of the time that I'm supposed to talk, so I'll just make a couple of closing remarks. The first is that I've presented only a few out of many results that are possible, and many results which are there in the preprint, but which are also kind of in preparation. For example, there's a whole lot of additional theory associated with quadratic networks, as you might guess from the fact that several of the kind of corollaries were about quadratic networks. The proof that the alternative equations actually capture non-degeneracy and transversality of fold and cusp bifurcations is something which isn't yet archived, but I hope to archive quite soon. There are many interesting open questions, for example, around how we make the various choices of matrices when we set up the alternative equations, about when some of the bounds we obtain are sharp. And I should mention that although all the results very naturally take the form of algorithms, and those algorithms really use primarily linear algebra and maybe some linear programming, the implementation of the results as algorithms is only very partial at the moment. So I will finish there. Thank you.